Good morning, students. So today's we start refraction through plane surface in the geometrical optics. Refraction through plane surface. So already in your lower classes you have studied the definition of a refraction, what it is. So when a ray of light travels from one medium to other medium, so rather than continue in the same, it will bend. This phenomena of bending of light when it passes from one medium to other medium, so that we say as refraction. So what exactly happens in the refraction? If this is our glass slab, okay, so we have the light has dual nature, as you know. If it travels in the form of wave, so this is one wave, second wave, and this is third wave. 1, 2, 3. 3 waves are passing in air medium. Let us consider in 1 second. In 1 second, 3 waves are passing through it. Okay. So next in 1 second, it has to pass through in the glass slab. So next in 1 second also, what it does? So here you can see this is one wave, second wave, third wave. Okay. So in 1 second, next 1 second, it is passing through in the glass slab. So what you are seeing here, this is one wave, second wave, third wave. So here also 3 waves are passing. In the sense, the frequency what we have here, the frequency is same. So it has traveled in fact less distance. Along with that, velocity is also, distance is less, velocity of the light has decreased. So we know that velocity is equal to, it is f lambda. Okay, wavelength is decreasing here, wavelength is decreasing. By what? Wavelength is decreasing by the same way, by what velocity of the wave is decreasing, by the same wavelength also, by same fold we can say wavelength also decreases. So that the frequency remain constant. Frequency remain constant. In 1 second here, 3 waves are passing. In the same 1 second, 3 waves are passing in this medium. So that the frequency of the wave remain constant. So what are the constant thing? One is as it get passed through into a glass medium, into a other medium. So what happens? The frequency of the wave remain constant. So color of the is because of the frequency only. So even I can say the color will not change. Frequency will not change. Color will not change. And even you can see here the same phase is continuing. Same phase. So in fact it has entered here. There is no change in the phase of the wave. The same phase. The wave has compressed. The wave is traveling in the same way. Only thing is it has compressed a little. That's all. Wavelength has decreased. Before, if the wavelength is this much, if this is the wavelength has a decrease. That's all. Wavelength has decreased. Nothing has happened to the frequency. Okay, frequency remains same, color remains same, the phase is same, So these three factors remain same if it passes through. So what is changing? Velocity is changing. Velocity is changing. Okay, then wavelength is changing. Intensity changes. So these things, velocity, wavelength, intensity changes. Whereas the frequency, color, phase, it does not change if a wave of light travels from one medium to other medium. So these will change, velocity, wavelength, intensity will change, whereas the frequency, color, phase will not change. As soon as it enters into the other medium, the wave appears as if it is compressed. Compressed. Wavelength is decreasing. By velocity decreases. By what fold the velocity is decreasing. By the same fold, the wavelength decreases. So because of that, frequency does not change. So next is absolute refractive index. So absolute refractive index with respect to vacuum. So when the ray is passing from vacuum to a medium, absolute refractive index. How you define it? Newton has defined this absolute refractive index as velocity of light in vacuum. Velocity of light in medium. That is, mu is equal to C by V. Okay, so it is. So I can write it as mu is equal to, it is a frequency into wavelength in air divided by, this is frequency into wavelength in the medium. So this frequency get cancels. Even I can write it as mu is equal to lambda by A divided by absolute refractive index. Either I can define it as a velocity of light in vacuum to the velocity of light in medium. So refractive index wavelength in vacuum, I can say. Wavelength in vacuum to wavelength in the medium. Wavelength in vacuum to wavelength in medium. So as you know, wavelength of red is greater than wavelength of violet. Wavelength of red is greater than wavelength of violet, and what you are seeing here, the refractive index and wavelength refractive index of the medium and wavelength of the medium, they are inversely proportional to one another. So therefore, so what it will be? Mu r. The lambda r is greater than lambda b. So whereas this is mu r into refractive index for red is less than refractive index for violet because of this. So in the two medium where the velocity of light is less, so that medium we say it as rarer medium, where velocity is less. So where velocity is less, so that we say as a denser medium, where velocity of light is more, so that we say as a rarer medium. So velocity of light is less, that medium we say it as a denser medium. Velocity of light where it is more, so that we say as a rarer medium. Okay. So if the temperature of the medium increases, what happens? If the temperature of medium increases, the molecules starts to move away from one another. If the molecules are moving away from one another, the density is decreasing. If the density decreases, so then it shifts, that it becomes comparatively, the density is decreasing. So because of that, the velocity of light becomes more. If the density is decreasing, it is becoming a rarer medium. It is becoming, comparatively, it is becoming a rarer medium. So as the temperature of the medium increases, the molecules starts to move away from one another. If the molecules are moving one another, then it becomes a rarer medium. Then velocity of light will be more there comparatively compared to, so what the temperature, what before we have and after if the temperature increases. So if the ray passes from one medium to other medium, relative refractive index. Relative refractive index. If a ray is moving from, this is one medium and it is other medium. So refractive index of the second medium, if this is mu1 and this is mu2. The refractive index of the second medium with respect to first medium. How we read it? We read it as mu2 by mu2 by, we read it as mu2 by mu1. So this will be mu2 by mu1. So velocity and refractive index are inversely proportional. So therefore it will be v1 by v2. So this is nothing but we can write it as lambda 1 by lambda 2. Refractive index and wavelength are inversely proportional to one another. Refractive index and velocity are also inversely proportional to one another. So, relative refractive index, rather than saying it as with respect to vacuum, if we say with respect to other medium. So, how we read it? Refractive index of second medium with respect to first medium. So, since velocity is inversely proportional, mu2 by mu1 is equal to v1 by v2. Okay. So then, principle of reversibility. Principle of reversibility. The same thing let us take. So we are reversing the ray. So how it is? By keeping a mirror exactly perpendicular to the path of it. We are keeping a mirror. So exactly perpendicular to it. So what happens? What the principle of reversibility says is it exactly retraces. It exactly, if it has come in this way now, it will exactly retrace the path. How it has reached to the mirror, in the same way, exactly it is going, it is reversing back. Exactly, it retraces back. So this is principle of reversibility. If this is mu1 by mu1 and mu2. So what it is? Refractive index of, so for first ray which is incident like this, refractive index of second medium with respect to first medium. It is mu2 by mu1. So for this ray, for a red color ray which is reversing back, for that, how can I write? Mu1 refractive index of it is going into the first medium, mu1 by mu1 refractive index of first medium with respect to second medium. For the red ray which is reversing refractive index of the first medium with respect to second medium. So what it is? It is mu1 by mu1 by mu2. So this I can write it as refractive index of second with respect to 1 is equal to mu2 by mu1. So this I can write it as 1 by mu1 by mu2. So this value I can write it as, so that if it goes up, exactly the same thing. I can write it as 1 by mu1 by mu2. What is this mu1 by mu2? Mu1 by mu2 is nothing but a refractive index of first medium. Sorry, 1 by it is 1 divided by refractive index of first medium with respect to second medium. So what I can say, refractive index of second medium with respect to first medium is equal to refractive index of first medium with respect to second medium. So this is our principle of reversibility. Refractive index of second medium with respect to first medium is equal to 1 by refractive index of first medium with respect to second medium. So this we say as a principle of reversibility. The ray retraces the same path if it is reversed. If it is reversed, in what way it has incident? In the same way, in the same path, it will go back. So that is our principle of reversibility. From principle of reversibility, we can refractive index of second medium with respect to first medium is equal to 1 by refractive index of first medium with respect to second. So next, if a ray of light is traveling from rarer medium to denser medium. So what it is? It travels a distance x in this. It travels a distance x in this. In a time t. In time. So this is of refractive index mu. So ray is traveling from rarer to a denser medium. So in the medium it is traveling a distance x in time t. So refractive index is equal to, it is c by v. So this is c divided by. So what I can write this as this v. V is velocity is equal to distance divided by time. So what distance it is traveling? It is traveling a distance x. In what time? It is traveling in a time t. So x by t. So this I can write it as mu is equal to, it is ct by x. Refractive index, of course, absolute refractive index it is ct by x, where c is velocity of light in vacuum, t is the time duration for which the ray has traveled in the denser medium, in the other medium, and x is the distance traveled in the other medium. So mu is equal to Ct by x. If you have two different medium, our expression is mu is equal to Ct by x. So we have two different medium. So for the same time, they have traveled in two different medium. For the same time, they have traveled in two different medium. Okay. So C is constant, T is constant. So what it will be? This Ct is constant. We can say it as mu into x is constant. If mu1 is the refractive index of the first medium and mu2 is the refractive index of the other medium, in two different medium it is traveling for the same time. So what it is? So mu1 x1 is equal to mu2 x2. Mu1 x1 is equal to mu2 x2. In a two different medium, mu1 and mu2, it is traveling a distance of x1 and x2. x1 in first medium, x2 in second medium, it is traveling for the same time duration. So then mu1 x1 is equal to mu2 x2. Okay. So next is two different medium we have, same distance they are traveling, but that distance is covered in two different time duration. What is time duration is different. Mu is equal to Ct by x. X is constant. Distance what it is traveling is constant. So C is constant. So mu is equal to, this is constant, some constant into T. In a sense, mu by T is constant. So it is mu1 by T1 is equal to mu2 by T2. So we can write it as mu1 T2 is equal to mu2 T1. The path what it is traveling is same in a two different medium. In the first medium, it is traveling with a time duration of T1. In the second medium, it is traveling with a time duration of T2. Same length, same path. For example, 20 centimeter distance in the medium. In the first medium, it is traveling in a T1 time. In the second medium, it is traveling in a T2 time. Then mu1 T1 is equal to mu2 T2. So if it mu1 T2 is equal to mu2 T1. So mu1 x1 is equal to, if time is constant, mu1 x1 is equal to mu2 x2. If distance is constant, then mu1 T2 is equal to mu2 T1. So main expression is mu is equal to Ct by x. Optical path. So already we have discussed it. So once again, just I will revise it. A ray of light is traveling in the medium a distance AB. It is traveling in the medium by distance AB. Okay. So this what distance it has traveled. So this we say as geometrical path. We say it as a geometrical path. So what is our optical path? Optical path okay. So what time it has taken here to travel this distance? If the same ray is made to travel in air medium, the same ray is made to travel in air medium. So what path, what distance it is going to cover? So that distance we say it as an optical path of this geometrical path. So here velocity in vacuum, or in air, it is c. For what time duration it is going? It is going in a time duration of t. So optical path is equal to, I can say it as c into t. Optical path is equal to c into t. So this t, what I can write? So this t I can write it as, so this is our geometrical path. D let us consider. Geometrical path it is. This much distance AB, distance is D. Its refractive index is mu. Refractive index of the medium is mu. Okay. So this T, how can I write? So it is velocity is equal to distance by time. Velocity is equal to distance by time, or time is equal to distance by velocity. So this distance by velocity. So this is c by v. So c by v is nothing but it is our mu. Mu into this d. What is this d? D I have taken it as geometrical path. Geometrical path. This is geometrical path. So it is optical path. Optical path is mu times the geometrical path. What exactly it is? Optical path is equal to mu times the geometrical path for a same time duration at t. So if a ray is traveling, if a wave is traveling in a medium of refractive index mu, so that we say as geometrical path. For the same time duration, same ray, if it moves in air or vacuum, what distance it is covering, so that distance we say it as optical path. So this optical path is mu times the geometrical path. Optical path is mu times geometrical path. Now we say Snell's law. Already you studied this. So if this is our medium, this is our incident ray, this is a refracted ray, incident ray, refracted ray, normal to the surface at the point of incident, normal to the surface at the point of incident. All these lie in the same plane. All these are lying in the same plane. Incident ray, refracted ray, normal to the surface drawn at the point of incident, all will lie at the same plane. In the same plane, all these will lie. If theta 1 is the angle of incidence and theta 2 is angle of refraction. Okay, if this is of refractive index mu. Okay, so what the second law says, second Snell's law says, sine of angle of incidence to the sine of angle of refraction, sine of angle of incidence to the sine of angle of refraction. So this ratio is a constant, and that is equal to refractive index of the medium, absolute refractive index of the medium. Sin theta 1 by sin theta 2 is equal to refractive index of the medium. So this Snell's law, we write it in vector form. The Snell's law, we write it in vector form. How is our first? So what the first law says? Incident ray, refracted ray, and normal to the surface all lie in the same plane. So this incident ray, I am writing as the unit vector along the incident ray, I will say it as I cap. The refracted ray along, I will say it as R cap. The normal to the surface, See, I am taking it in the upward direction. Normal to the surface, I am taking in the upward direction. So this is our n cap. The unit vector along the normal to the surface, I will take it as n cap. The unit vector in the direction of the incident ray, I will take it as I cap. The unit vector in the direction of the refracted ray, I will take it as I cap. Okay. So now, this Snell's first law, I can write it in vector form using the vector triple product. How it will be? So this is I dot I cap dot. It is R cross n. I cap dot R cross n is equal to 0. I'll explain now. So, another way I can write it as R dot I cross n is equal to 0. Or n dot I cross R. So how it is? R cross n. R cross n. If the cross product of these two vectors, if we take. So if we R cross n, if we take like this, how it will be? A vector is coming outward. Vector is coming from right hand thumb rule. If you find the direction of the resultant of these two. Direction of resultant of these two. Any two you can take. Let it be I cross R. I cross R. From I to R you are taking. From I to R you are taking. This is the angle. So it is coming out in the. It is coming out of the board like this. The direction of this I cross R will be in this way. I cross R will be in this way. Okay. So now you see. I cross R, you are getting one vector which is like this. If I see this one, so it is coming out like this. The cross product of I and R are like this. So now n and resultant of these two. N and resultant of these two. N and this normal and resultant of these two. How they are? They are perpendicular to one another. They are perpendicular to one another. The dot product of these two. So this I take this these two I take it as k cap. Some k I will write. Okay, these two. Some k I will write. So this is dot n cap. So this is our k. What I said, the resultant of these two k cap I have taken. And so this is n. N and k, they are 90 degree to one another. So in the sense, n dot k is equal to 0. In the sense, this n dot I cross R is equal to 0. When this is possible, n dot I cross R is equal to 0, when it is possible, if I, R and N, if all they are lying in the same plane, then only this is possible. So I cross N, here also you can see I cross N. So there is I cross N from I to N. So it is coming out like this. Okay. R and I. Once again, they will be. It is like this. R and N, they are 90 degree to one another. R and N are 90 degree to one. Sorry, R and K. Something if I resultant of these two, if I take R and this, they are 90 degree to one. So like this, if incident ray, refracted ray, and normal to the surface, if all they lie in the same plane, so then only this is possible. So any of these, let us write. So all these denotes the first law of Snell's law. So this is vector form of first law. I dot R cross N. So R dot I cross N. N dot I cross R. So whatever it is, so these triple product of these vectors will be equal to 0. So that shows the incident ray, refracted ray, and normal to the surface, they lie in the same plane. Then only the triple product of these three vectors become equal to 0. So because of that, so from this way we can say the vector form of the Snell's first law. Triple product of I, unit vector I, R and N. So this represents your Snell's first law of Snell in vector form. So second law, if this is our mu1 and this is our mu2, so it is mu1 sine theta 1 is equal to mu2 sine theta 2 is our normal Snell's law. Mu1 sine theta 1 is equal to mu2 sine theta 2. So this I have to write it in vector form. So this I have to find out the value of sine theta 1 and sine theta 2. So these values I have to write sine theta 1 and sine theta 2. Okay. So now sine theta 1 is angle between incident ray and normal to the surface. So this is angle between these two. We will find out the cross product of these two. How it will be? Cross product if we are taking, so angle, what is? If this is our normal in this direction, so this is our incident ray, but while taking the direction, we have to extend it in this way. So this is our theta 1. So this is, I can write it as 180 minus theta 1. This angle is 180 minus theta 1. So this is our n cap, and this direction is our I cap. I cap is in this direction and n cap is in this direction. It is 180 minus theta 1. So now I will write it as I cross R. What it will be? Magnitude of I cap, magnitude of R cap, sine theta 1, sine theta 1. So I to R, angle is from I to R, it is coming out like this. So I will take that direction as some k cap. Some k cap. Its direction, the resultant direction is around some k cap I will take. So magnitude of I is 1, magnitude of R is 1, sine theta 1 into k cap. This is our I cross R. So I cross R is equal to sine theta 1 into k cap. I want a sine theta 1 value here. So what I do? So this k cap I will take here. Unit vector along incident ray, unit vector along refracted ray. K cap is unit vector perpendicular to the resultant of these two. It is sine theta 1. So sine theta 1 is equal to I cross R. So similarly, I have to find out this sine theta 2. Sine theta 2. So here I have taken n. It should be n cap because theta 1 is angle between these two, not R. It is n. N. Isn't it? So it is angle between I and n. It is I and n. Similarly, so this is theta 2. This is theta 2. So what angle I take to find out? This will be 180 minus theta. 180 minus theta from here to here. So what it is? R cross into n. So this will be, so this is magnitude of I, magnitude of R, R cap. This is n cap into sine theta 2. Sine theta 2. This is also coming out in the outward direction. Outward direction, I have taken that as k cap. Outward direction. Resultant of these two is in the outward direction. From R to n, it is coming in the outward direction. So this is 1. It is into 1 sine theta 2 into k. So R cross n is equal to sine theta 2. So divided by k. R cross n e by k. Is equal to sine theta 2. So substitute these things in our Snell's law. So this is the value of sine theta 1. It is value of sine theta 1. I can write it like this. So value of sine theta 2. When this is theta 2, I have to take from R to n. So this is 180 minus theta. So sine theta. So if you substitute here, this 180 minus theta, it will be sine theta only. Because of that, I have kept it like this only. One sine 180 minus theta will be sine theta only. Because of that, though 180 minus theta 1 here, 180 minus theta 1 here, I have kept it to sine theta 1 only. Because sine of 180 minus theta 1 will be once again sine theta 1. Here also 180 minus sine theta 2. 180 minus sine theta 2. Sine of 180 minus theta 2 will be sine theta 2 only. So that is why I have kept it like this. So substituting these values in our Snell's law. What is our Snell's law is mu1 sine theta 1 is equal to mu2 sine theta 2. Mu1 sine theta 1 is what is I cross n by k is equal to mu2 into r cross n by k. So mu1 I cross n is equal to mu2 into r cross n. So this is our vector form of Snell's second law. Mu1 instead of sine theta 1, I have I cross n. Mu2 r cross n. This is vector form of Snell's second law. So next is this is our medium of refractive index mu. So there is a incident ray at this point, refracted ray reflected ray is and this is our refracted ray. If I draw once again, so how it will be? Incident ray, this incident ray and refracted ray, they are perpendicular to one another. They are perpendicular to one another. So then how it will be? If this is our angle theta, then this also will be theta. So let us consider this refracted angle is some r. Okay. So it is 180. This line is 180 is equal to 90 plus, this is 90. They have mentioned that incident ray and refracted ray are 90 degree to one another. 90 plus theta plus this r. Okay. So then what it will be? If it comes this side, so this is 90 degree is equal to, so theta plus r. R is equal to, it is 90 minus theta. So it is our incident ray, theta is our incident ray. R is equal to 90 minus theta. What is our Snell's law? It is mu is equal to sin I by sin R. What is our incident ray? It is theta, sin theta, divided by sin. So R is nothing but it is 90 minus theta. So this is sin theta divided by, it is cos theta. So this will be our tan theta. Refractive index is equal to tan theta when the condition is the incident ray and refracted ray, they should be perpendicular to one another. If they are perpendicular to one another, refractive index is equal to tan theta. If it is moving from rarer to denser, from air to a medium of refractive index mu, it is mu is equal to tan theta. So that itself, if it is moving from denser to rarer, then same thing, mu is equal to cot theta. From denser to rarer. Listen, from medium to vacuum. Medium to vacuum, if it is going, mu is equal to cot theta. If it is going from vacuum to medium, then mu is equal to tan theta. Mu is equal to, from vacuum to medium, mu is equal to tan theta. Medium to vacuum, mu is equal to cot theta. we have one medium. The object is somewhere here in the denser medium of refractive index mu. It is in the denser medium. Object is in the denser medium. So what it is? One ray will go from the object, a source of light, let us consider. One ray is going normally like this, whereas the other ray will go from denser to rarer. It is going, as you know, it moves away from the normal. It moves away from the normal. If it is extended backward, if it is extended in the backward direction like this, it appears as if coming from here. So this is where image will appear for a person who is seen from here. Who is seen from here. For that person, though the object is at this point, the image will appear at this point. Image will appear at this. It is shifted in the upward direction. It appears as if shifted in the upward direction, which we say as, since it is happening normally, so this itself we say it as a normal shift. So this is our normal shift. As a shortcut to find the expression for this normal shift, as a shortcut, we will use refraction through the curved surface. What it is? Refractive index of the image medium divided by V minus refractive index of the object medium divided by U is equal to, it is mu I minus mu O by R. So this is our, for a curved surface. Of course, here it is not curved. The surface where the refraction is occurring is not curved, but this very easily we can use as a shortcut for this. So here our R is infinity. R is infinity. So then this whole term becomes 0. So what I can write? So mu I by V minus mu O by U is equal to 0. Okay. So ray is, let us consider ray is going from a medium to air. Air in the sense its refractive index is 1. So where the image is forming, mu I, where the image is forming, a person is seeing in the air medium or vacuum medium. So its refractive index is 1. Okay. So where the object is in the denser medium of refractive index mu. Object is mu O. Is mu. If this is our P, so this Pi, so this is our image distance. You can see the incident ray is going, in this way. The ray is going in this direction. Okay, so for that, what we have to do? If the ray is going in this direction, the sign conventions that we are using in the curved surface, we can use here also. So what it is? U is equal to it is PO. So we have to measure it from here P to this, opposite to the incident ray, opposite to the incident ray.
Okay, opposite to the, if the incident ray is like this, we have to measure it opposite to it. So therefore we are writing it as, if this is height of the, or depth, if I take opposite to the incident ray is like this, from the pole we have to measure, from P to O we have to measure, so therefore it is minus H, minus PO minus H. So V is equal to, it is minus PI. V is equal to minus PI. Substituting these values, what is 1 by V is minus PI divided by, sorry, minus it is mu by minus H is equal to 0. It is 1 minus Pi plus mu by H is equal to 0. If you take it that side, so we want the expression for, so it is 1 by minus Pi is equal to minus mu by H. So this get cancels. So Pi is equal to reversing it, it is H by how much this distance? If this distance is H, what will be this distance? This distance is H by, if total distance is H, this will be H by. So what is this? It is real depth. H is real depth, and this is apparent depth. Real depth and apparent depth. So this is our apparent depth, and it is a real depth. Apparent depth, I can write apparent depth is equal to, it is a real depth divided by mu is equal to real depth by apparent depth. Mu is equal to real depth by apparent depth. Apparent depth is equal to either this you can use, or mu is equal to real depth by apparent depth. So this distance we write it as H by mu, and this distance we write it as H. So mu is equal to real depth by apparent depth, or Pi is equal to H by mu. So this is normal shift. If the object is in the denser medium and you are viewing it from a rarer medium. In the tomorrow's class, what happens if the object is in the rarer medium and it is seen through the denser medium? What happens? How will be the normal shift? So that we will see in the tomorrow's class.